Okay.
This is the same idea for Laplace transformation.
They're very closely related to each other. We'll talk a little bit about that. But the Laplace transform and the Fourier transform very similar to each other. Fourier transform turns out to be just a special case of the Laplace transform. So maybe for a second, one of the things that I should do in looking at this is, so I think on my phone I have, let's see, I think I have an oscilloscope here. Okay, I do. All right, so I'm going to try to. All right. Oh, my virtual background is going to screw it up. Okay. Do you guys see that?
Is that an app?
It is, but
Is that on the App Store?
it is.
I had to look into that. I didn't know they had stuff like that.
Yeah. Well, they got all kinds of crazy stuff, I guess. All right. How do I turn off my background? Yes, there we go. Okay. Thank you. All right. So if I hold that up there, basically what that's doing is my voice is turning into a voltage, right? Coming out of the microphone. That's what a microphone always is going to do. If I stop talking, you see it go blank. Basically what's going on there, that's a periodic waveform. Right? It's got a sum of sine waves that are inside of it. Looking at that picture is not necessarily very useful for me in a lot of ways, because what is that? I can make a mathematical model of that, but one of the things I typically want to do is look at something like that and get a sense of what's in it, right? So, you know, what kind of thing would I want to be able to do? Well, my voice has certain frequencies to it, or certain ways that the frequencies show up at least. So does yours, all right? And you can begin to do something like, let's say, if I switch over to here, all right, something like this, where I took a screenshot from this particular device here, and I say, okay, well, one thing I might want to do is put that waveform through something called a spectrum analyzer. Now, what does anybody know? Anybody ever heard of a spectrum analyzer? What is that? Well, what it would do is it would tell me basically what frequencies are contained within that signal. So it tells me the frequency spectrum. So effectively what it does is in most cases, what it does is it computes something called a fast Fourier transform, which is an algorithm. So some of you guys may have heard the term FFT before. That's something that if you've goofed around with Arduinos and stuff like that, that you may have heard, or Raspberry Pis, maybe you've heard that term. Right? What this is a tool. In particular, I'll take the first F off. Right? The Fourier transform is a way of analyzing a signal like that in the time domain. So in other words, this x-axis here, for us, we said for all of our ECE type of problems, that axis is usually t. All right. Well, that means that this is a time domain signal. It's a signal we can measure in the real world. What I often want to do is I want to see what that thing looks like in the frequency domain. Okay. Now, the spectrum analyzer basically tells me at what frequencies are present in this signal. So if I had something like a voice recognition algorithm, right, what's it doing? Well, basically what it's doing is it looks at the patterns of the frequencies, because the patterns of the frequencies can go along with what we call phonemes, okay, is the term that's used for it. Basically, the sounds that your voice makes, right? So when you say the letter A, there's a particular set of ways that the frequencies look like when you say that. All right, so basically a voice recognition algorithm would do something like this, where it would look at what comes out of that spectrum analyzer. All right, so we're gonna talk about, it's a very useful process, because even, and this is the context of, I want to analyze the spectrum to build a voice recognition algorithm. Well, if I had something like what you're going to look at in the project, I'm going to give you something where I say, okay, you're going to do PWM for so pulse width modulation to drive a robot. Okay. Not a real robot, but just to design it, I have to be able to do some analysis in the frequency domain to be able to do that kind of work. So the frequency domain, meaning somehow I want to get this signal mapped over into something that shows me as a function of frequency, what frequencies are there. All right, that's a useful thing for me to think about how to design things like filters and stuff like that. Okay. So this is the Fourier transform is the tool that allows us to figure out what frequencies are present. Okay. So what I would typically have is, and when I look at something in the frequency domain, I look at something like this. So this is another app that you can get. So there's let's see, I'll try it real quick. So the FFT Spectrum is what this guy is called. So I'll turn on the camera here again so you guys can see it. Okay. And I'm not sure. Okay. All right. So if you look here on the frequency axis there, what you see is how well you can see that. But those are frequencies in hertz. And what you see every time I speak now, basically you see what I would call is those kind of look like impulses, don't they? Kind of. I mean, they're sort of like impulses. They're a little bit more. They're broader, maybe, right? But they still kind of look like impulses. They're basically peaks at certain frequencies. So those are the frequencies that are there in my voice. Okay. So every time I speak, you see something new appearing because there's a new set of frequencies that are appearing. And what do you notice about those frequencies too? Every time I speak, it looks like they're kind of sort of spaced equally, aren't they? So I have to say something to see that, right? If I look at this sort of screenshot of it here, you can see it too, right? They look kind of spaced equally, right? Like the spacing between these points, the spacing between these 2 points and these 2 points looks pretty similar, doesn't it? What does that mean about those frequencies? They are harmonics. They're harmonically related because that waveform that we were looking at here on the previous slide, this guy is periodic. And so there's going to be harmonics in that signal. So there's multiple sine waves that are harmonically related inside of it. And so when I look at this, I see harmonically related stuff. In this case, it looks like maybe my, this particular waveform here, I put it 412, right? I can represent this thing as maybe a Fourier series of some fundamental, right? And I don't know where that fundamental would be. Maybe it's this guy right here. That looks like the lowest frequency I have in that signal. So what we've learned about is the Fourier transform, or sorry, the Fourier series. That's what we've learned about up until now, okay? And and that's what you guys have on the homework right now. What we want to do is transfer that knowledge over a little bit to this idea of a Fourier transform where I can look at these things as a function of frequency. That usually helps me from a design perspective. And the one thing about a Fourier series is it only applies to periodic waveforms. Fourier transform applies to any waveform, whether it's periodic or not, okay? And that's important. So, and somebody asked the question, is it related to a Laplace transform? You probably heard about those in differential equations. Yes, they are related to each other. All right, there is a clear relationship that we can talk about. So, all right, what we talked about on Monday was basically a lot of what you have in the homework this time, which is all about how do I calculate the Fourier series coefficients. So where we ended up last time was we looked at something like, right, something like a square wave, right, where we had, where is it here? We went through, if I had a square wave, it's very similar to what you have in the homework, right, where in the homework what you have is something similar to this, not quite the same shape, right? In other words, I think what you see in the homework is I give you something that is a different height, maybe it's a height of 1, and it's not it's not that height for half the period. It's maybe 10% of the period or quarter of the period or something like that. And then I give you another waveform where it's looks like this. Right, I give you another waveform where it's, I think, repeating like so. Okay, and it repeats and does something like that. Okay, it's the same basic approach for the waveform that you have in this problem that we did in class. What do I have to do? Well, what we did last time is we said, okay, when I have a waveform like this, what I have to do is I have to write a function for x over the period. And I got to figure out what intervals do I need to integrate over that period. And that'll give me the alpha n components. And what we talked about last time is in putting this into MATLAB, what I end up asking you to do is to determine the alpha n vectors. And then basically use those both to plot the function. So we walked through that in detail on Monday. And then we also talked about once I have the alpha n values, how do I get the b and the c and the theta? All right, so if you need to know how to do that, you can go back and look at Monday's class, right? Because Monday's class goes into that in detail, how to make those plots. All right, that's so basically what we were left with is the whole idea with the Fourier series. I can figure out those coefficients. I can then rebuild the function. Okay, we're doing something a little bit different here today. Okay, so let's jump over to where we were. So this idea is if I take a waveform, so this guy I've shown right here, this is the waveform I get in the real world. Right, this is some real world signal. Could be my voice, could be a voltage that I measure on the grid, could be some signal coming from a sensor. Right, I get this signal here that is a function of time. Its x-axis is the time domain. This guy in this picture is periodic. He's made up of a sum of 3 different sine waves. What this is showing here is what I have when I'm in the frequency domain. So what you have is basically impulses that sit at the frequencies where this original signal had energy. So I have some at this. So which one of these? Let me ask. I got 3 waveforms that are here. Which one is the lowest frequency one? Yeah, this guy is the lowest frequency. So there's an impulse sitting at that low frequency, close to 0. And there's one at the middle frequency where this guy is. And then there's one here at the high frequency where this is. So what we got to do is figure out, how do I jump from this to this? That's what the Fourier transform does, is make the jump from there to there. Okay, to figure out what frequencies we have. And that's, again, that's useful because let's say, for instance, that I didn't want this frequency. Let's say I wanted to get rid of that term. But again, the way I get rid of that term is I have to take this original signal here in the real world and pass it through something like a filter. So I got to know what's here so I can find out, how do I make a filter that only keeps this signal and gets rid of the other one. So I got to know what's there to be able to do that design. That's what we're going to use this kind of Fourier transform tool for. All right, so let's kind of think about how we would motivate this. All right, so let's look at what I have right here. So a pure cosine. And let me go back to full screen here. All right. So here I have this pad. Okay. All right, I've got this waveform right here, 3 cosine 2 pi t minus 30 degrees. And what I want to do is I want to represent this guy in the frequency domain. So I want to show so the frequency domain idea is I want to show this guy as a function of omega. All right, so I want to show what frequencies this guy has some energy. So let me ask you this. At what frequencies does this guy have, says x of t, what frequencies does he have energy? What frequency is something going on?
2 pi.
2 pi. Now, the question is, it probably all depends on which way I write the waveform, right? We said there's 4 different ways to express this thing, right? So we talked about this before. the ways in which to try to express this guy, I've written it in this sort of first approach, but I could write it 3 other ways. The one that's actually used with the Fourier transform is always this one. All right, this x of t is equal to 2 rotating vectors, one rotating positive, one rotating negative. So 3 cosine 2 pi t minus 30 degrees. This is my approach 1 here. I want to get this into my approach 3, which is the Euler approach. So Euler is my approach 2 or 3, sorry. So how do I express this in that form? What do I do to express this in that form? Well, what is the approach 3? Approach 3 is this guy here, right? So I think I heard that. So it's 3 over 2 times what? E to the negative j 30 degrees, okay, times e to the j 2 pi t. That's one of the 2 rotating vectors, right? What's the other rotating vector? Conjugate here. So 3 halves e to the j 30 times e to the negative j 2 pi t. And which one is the positive rotating one? Which one rotates in the positive direction? The first one, the one with the positive frequency, and the one with the negative frequency is going the opposite direction. So that's my vector, and I say that my alpha 1 here. What's my alpha 1 and so I say alpha 1 and alpha minus 1 because this guy, first of all, this is a Fourier series, but it's a very simple Fourier series, right? How many harmonics does this guy have? 1, only 1 harmonic here. So there's an alpha 1 and an alpha minus 1. Alpha 1 would be 3 halves e to the negative j 30 degrees, and alpha minus 1 would be 3 halves e to the j 30 degrees, like that. All right, those are my 2 vectors. So what we're going to do is always get things into this form. The Fourier transform kind of assumes things are always in this form. So what we end up doing is if I look at that expression, if I look at that result right there, okay. If I try to ask you at what frequencies does that thing have information, what frequencies would you say this guy has information at?
2 pi n.
Well, not 2 pi n in this case, because in this case I only have 1 frequency, right? So 2 pi t. So this guy had a frequency omega equals 2 pi, right? When I expand it into this form, it actually looks like it has frequencies at omega 1 equal to 2 pi. And what's the other one?
Negative 2 pi.
Yeah, negative 2 pi. All right, so basically it looks like if I said there's energy at those 2 frequencies, what's the useful information? If I wanted to compact this to say, I want to capture the information that is contained in this waveform. All right, and this is what's hard for you guys to wrap your mind around is you haven't really had to think about this enough. Cosine 2 pi t minus 30. How many data, if I had to sample that waveform, how many data points exist in time in that waveform? Infinite. There's, think about that. It would take all the storage space in the world to store a waveform, right? Because it's a time domain waveform. But if I wanted to recreate that waveform, what do I need to know? If I told you, I want you to invent a compression algorithm for cosine, right? So I don't want to save all the data from that cosine. So a compression algorithm would cut it down to the simplest thing I could save about it and still be able to recreate it. So what information would I need to get out of this cosine to be able to recreate it without having to save all the time series data? Period or the frequency? What else? the amplitude and the angle. If I get the amplitude, if I get the angle, and I get the frequency, I could recreate a million data points from that thing. Okay. So if you think about this, what I'm going to say is the Fourier transform captures all of that information and says, at the frequency, at certain locations, I have some information that I'm trying to keep. The information that I'm trying to keep is, let's say in this case, 3/2 e to the negative j30. That information is useful to me. And at what frequency does that information apply? At what frequency would that apply?
2 pi.
2 pi, right? 2 pi. So how about one way to express that would be to say that, let's say this guy, so the picture we had on my phone, right, was basically, you were looking at the magnitude specifically. But I'm going to write it this way. So you were kind of looking at impulses, right? What you saw was these waves that to me kind of look like impulses, right? Impulses are supposed to be really high and really narrow. Well, these guys are peaky like that, right? They're peaks and they're not maybe as narrow, but they're kind of like impulses, right? So when I think about it, I'm going to say that this thing has information at those frequencies. So I'm going to use an impulse function. And I'm going to say I have that. And then I'm going to say the other place where I have information is at what frequency? What's my other one? What other location would I have information? So some of it is at 2 pi. What's the other frequency here?
Negative 2 pi.
Negative 2 pi, right? So e to the negative, so e to the j, 30 degrees. And I'm going to put this with an impulse at omega plus 2 pi, like that. Okay, so this is the way I'm going to write the Fourier transform. Now, what I want to do is I want to think about how would I graph this function. All right, so let's forget about for a second. Let's just say x of omega was this 3/2 delta of omega minus 2 pi plus 3/2 delta of omega plus 2 pi. Okay, let's say it was that. And let's say I wanted to generate a graph of this thing here. So I want to draw a graph of x. Now, first of all, because it's a function of omega, I have an omega axis, right? For my x-axis. So how would I plot this guy down here on the bottom? So I got two impulses, right? Where would I put the impulse? My impulse or Dirac delta, I guess. That's what delta is. It's that Dirac delta. It's an impulse. So if I said delta of omega minus 2 pi, where would that be located? What frequency omega would that be located?
Would it be shifted to the right at 2 pi?
Yeah, so at omega equal to 2 pi, right? This would be 2 pi. This guy would be 3/2 tall. Okay. And then what about this one here?
Shifted to the left 2 pi.
Yeah, this guy's his exact image, minus 2 pi with a height of 3/2, like that. All right, so what I'm trying to do is I'm trying to capture where this signal has energy, and I want to make that graph of where it has energy. Now, by definition, we make the graph assuming this approach number 3. All right, assuming that we have it in that form. So we have something with the positive and the corresponding negative frequency together. All right, that's just sort of the standard approach of the way the math is defined. I said because the math usually gets easier when we use the complex form. So we tend to use that, okay? All right, but what I did skip something a little bit here, right? Because this is actually 3/2 e to the j 30 degrees 3/2, or this is -30, this is 3/2 e to the j 30. That's not what I plotted right there. All right, so let me come back to this. I want to get to this question right here. All right, complex functions of a real variable. All right, it's described here in chapter 4. All right, it's a pretty easy concept. It's not that difficult, but if I gave you something like x of omega equals what I just did right there, 3/2 e to the j or -j 30 degrees times delta of omega minus 2 pi. How should I graph that? All right, I'll use this example, right? This is from something different, right? H of omega is this guy. How should I graph that? If I said to you, graph versus omega 4e to the j 60, how would you graph 4e to the j 60? Can you graph that? Think about graphing. So this is a function of omega. It's a function of omega because I have this impulse thing. Okay. So at a certain frequency, in this case, at what frequency do I have energy for the waveform I've got here, for this h of omega that I've got here? At what frequency do I have some information? 2 pi 60. Okay. Omega equal to 2 pi 60. At omega equal to 2 pi 60. So I guess the other way to write this is I could say this h of omega is equal to 4e to the j 60 for omega equal to 2 pi 60 or 0 otherwise. That's sort of how to think of that, right? How would I graph that? How do I graph 4e to the j 60 at omega equal to 2 pi 60?
Would you use one graph for magnitude and the other graph for the angle?
Yeah, one graph for magnitude and one graph for angle, right? That's the basic idea. So when I can't graph e to the j 60, there's no meaning to a graph for that. But if I think about it, if I take the magnitude of, so magnitude over here, 4e to the j 60 degrees, what is that? Yeah, this guy, well, the magnitude of this is 4, yeah, and if I think of the angle of 4e to the j 60, the magnitude or the angle of that is 60 degrees. So how would I end up drawing that? H of omega here, this guy, if I think about this, would be 4 at the location omega minus 2 pi 60 degrees, like that. So this guy would have a magnitude of 4 like that, and this would be at 2 pi 60. The angle of h of omega would be equal to 60 degrees at omega minus 2 pi 60. 2 pi 60. Like that. So that what I would do is I'd make an impulse here and I'd label its height as 60 degrees. Like that. Makes sense? Okay, so basically there's no way, so when I have, in this case, what I'm calling this is a complex function of a real variable or a real argument. This is saying I have a function of frequency that is complex. So in other words, the value of h in this case is a complex number. It has a magnitude and it has an angle, but I compute h as a function of omega. So I put a particular value of omega in and I get a magnitude and an angle out. So when I plot it, I have to make separate plots of this. Now there's a thing in 2112 that you may or may not be learning. I don't know. Bode plots. You guys talking about that? Does that come up? Okay. Not yet. Okay. And it may not, I don't know. But have you seen or heard of filters at all there? In the lab. Okay. So at some point you'll come across these. So we will actually talk about the Bode plot thing a little bit in here, but there is essentially if I have a circuit that is a filter, what I want to know is I want to know what frequencies does that filter work? Because a filter comes, when you have a circuit that has impedance, impedance is a function of frequency. All right, so we'll think more about this concept. It's a pretty straightforward idea. If I have a complex number that's a function of frequency, I have to plot its magnitude and its angle separately. I could plot its real part and its imaginary part too, right? No reason I can't, but that's usually not as useful as the magnitude and the angle piece. Okay. All right. So what I was trying to get across here is if I'm gonna get rid of this last thing here. All right. What I really should be plotting when I plot this thing is I plotted the magnitude here, and then I can also plot the angle of this thing here. So angle of x of omega. And the angle of x of omega, let's see, what's that going to look like? So in this case, I have stuff at 2 pi and negative 2 pi. What's my angle at 2 pi? So what's the angle of the component that's at 2 pi in this picture? Negative 30. So at 2 pi, I have an impulse that's going to be at negative 30. And at negative 2 pi, I have something that's going to be at 30 degrees. Okay. So pretty straightforward concept. It's not that hard to sort of get. And we formalize it like this. If I have a periodic waveform, okay, I can use this impulse function that we've defined. All right. So the impulse function is a useful thing. It allows me to do a lot of stuff. It's a powerful kind of basic signal I can build with. So I'm saying I can use the impulse function to build something for a Fourier series. So if I have a periodic signal that has frequencies at harmonically related frequencies, or information at harmonically related frequencies. So if I have x of n, or sorry, x of t, that has info at n omega naught, then I can express the information that it has at those frequencies using this relationship. So basically, this guy is another infinite sum that says from n equal negative infinity to infinity. So what am I saying? If I n equal negative infinity to infinity, what's n again? What did I define n to be? It's the harmonic number. Yeah, it's the number of the harmonic, right? So I'm saying I'm going to get from n equal negative infinity for all of the places where I have information, I'm going to get an impulse in this graph, right? That's what this thing's going to have. Okay. So, all right, let's take a look at something like this guy. Okay. Let's say I wanted to generate the Fourier transform for this guy. Okay. So this is a Fourier series too, right? First of all. So we said with the Fourier series, I had kind of a couple of steps for this. The first step was to do what? If I wanted to generate the Fourier series information, that means I want to get the coefficients, right? So how do I get the coefficients? I said there were 2 steps for me, right? The first step was what? What do I have to do in looking at this? Find the fundamental frequency and what frequencies are in this thing. And then I basically find the coefficients at those frequencies. So looking at this guy right here, what is the fundamental frequency? Well, I can use that greatest common divisor thing, but I think you can probably tell, I hope you can tell. I like to say the fundamental frequency in hertz. So omega naught, I'm not going to focus on that. I'm going to get to omega naught. I want to say, what's f naught here? For the waveforms, so I've got 3 signals here, this guy, and this guy. What's my fundamental here?
60.
60 hertz. Yeah. 60 hertz. Okay. So that means this guy is 2 pi 60. All right. So if that's the case, what harmonic numbers do we have here? Let's go through our n values. Which ones do I got? Well, I have 1. N equals 1 corresponds to an omega value at 2 pi 60. What other frequencies do I have here? I have a 0 term. And what frequency is that? 0. Yeah, DC. So this is DC is the other term I'll use for this one. Okay. Do I have an n equal 2? That would be 2 pi 120. Do I have that? No. But I do have a third, which is 2 pi 180. All right, so I have all of those terms. Now, what I want to do is I want to get the alpha values. I want to get the alpha ends at those frequencies. So that means I gotta look at this thing. I got to figure out how to convert this into the forms of my series. Okay. So how do I convert this into the different forms of the series? Well, 5 is 5. That's nice and easy. What about the 4 cosine 2 pi 60 t plus 60 degrees? What do I have to do to that? I want to get it into that form of the series where it's the sum alpha n e to the j n omega naught t. All right, that's the form I want to get this thing into. So what do I do with that guy? The 4 cosine 2 pi 60 t. Yeah, so looking at this, it's which form is it in? That's the one thing probably always want to ask, right? Looking at this is that shifted cosine. So I have a Cn and a theta n, right? So looking at this, I see that for this guy, I have a C1 equal to 4 and a theta 1 equal to what? 60. Okay. So 4 cosine 2 pi 60 t plus 60 degrees is equal to 4 over 2. All right, what else? How do I get this into that alpha form? So it's basically using that Euler's identity thing, right? So 4 cosine 2 pi 60 t plus 60 degrees, that's 4 over 2 e to the what? E to the j angle, which is what? 60 degrees times e to the j 2 pi 60 t. All right, that's the positive rotating vector. What's the negative rotating vector look like? Conjugate of that. So 4 over 2 e to the negative j 60 times e to the negative j 2 pi 60 t. Oh boy, out of space. Okay. So that's how I expand this one. What about the 6 sine 2 pi 180 t? How would I approach that one if you didn't know any better? What form is this guy in? My third harmonic term is in which of the forms that I've got here? Which form would you say that one's in? So what's that? The sine cosine version of it, right? So I can look at that one. It looks like it's in this form. All right. So what I have is put this here. All right, so I've got 6 sine 2 pi 180 t, like that. This guy is in that a cosine 2 pi 180 t plus b sine 2 pi 180 t form, right? So looking at that, right, and I should say, not just is this A, but I should say A3 and B3, because this is my third harmonic, right? So what's A3? A3 is 0. What's B3? Well, B3 is equal to 6, right? So then I can go to those formulas over there to try to figure out how to map those over into angles for myself, right? So C was equal to basically A, so C3 is A3 squared plus B3 squared, like that, okay? Which, if I do the math here, this shouldn't be hard to do. What's that going to equal to? 6, all right? Theta 3 would be minus tan inverse of B3 over A3. Whoa, that's not fun, is it? Why not? There's a 0 on the bottom, right? Now, technically, you can go, there's some definitions for that. Now, one of the things I also listed, I did this probably on the first day, and it probably went over most of your heads at that point, is when I'm looking at something like this, I said that I can actually put this guy as kind of in vector form, okay? So I can say I've got C, so C e to the j theta relates to A and B. So I can say that this guy is actually C3 e to the j theta 3 equals A3 minus J B3. Okay, so that means it's this guy is equal to 6 e to the j angle, whatever that is. And that's also equal to 0 minus J B3. All right, and I know B3 is 6. Like that. Using that, how can I figure out the angle of this vector? What is the angle of that vector right there? Without doing any math, just looking at that. What's negative 90 degrees, right? Because it has so negative J6 points straight down. So this guy has an angle of negative 90 degrees. So basically from that, so this would be useful to you probably when you're doing your homework. You're gonna this way is useful if I can put things into this form, right? A plus B. I can ask MATLAB what's the angle of that vector, and it'll tell me that. All right, that's probably an easier way to do some of the ones that you have on the homework right now. All right, so that tells me this guy here. If I wanted to put this, now that I've got my C and my theta, all right, how do I get that into the alpha form of the series? How do I get this to the alpha form of the series? So 6 sine 2 pi 180t is equal to, we've just found that there's a C3 of 6 and a theta 3 of minus 90. Okay. So how do I write that in the alpha form of the series, if that's the case? 6 over 2 e to the negative j 90, yeah, and then e to the j 2 pi 180t, and then let me put below it 6 over 2. What do I do to the angle on this guy? Just the opposite, right? E to the j 90 degrees, e to the negative j 2 pi 180t, like that. Okay. All right. So now I've written the whole thing out. So I derive from myself here. All right. So I have 5. So my DC terms, let's go down. Let's go here. So we've defined a couple of things for ourselves. So we said we had certain values of n. Oops. Certain values of n. So I had n, omega, and then I have my alpha n values that I've figured out. Okay. So let's go through that. All right. So the n values that I have here, and let's write this whole thing out neatly for ourselves. All right. So x of t is this whole thing. So we figured out for ourselves that x of t is equal to 5 plus 4 over 2 e to the j 60 degrees times e to the j 2 pi 60t plus 4 over 2 e to the minus j 60 degrees times e to the negative j 2 pi 60t plus 3 over 2 e to the j negative 90 e to the j 2 pi 180t plus 3 halves e to the j 90 times e to the negative j 2 pi 180t. Okay. All right. So we did all that. We did a lot of work actually. All right. So now in the form of the series where I have the complex form, I have positive and negative frequencies, right? So what are the harmonics? You guys said I had something at 0, 1, and 3. So if I go into the complex form of the series, it's not just 0, 1, and 3, but where else? Yeah, I'll have them, I'm at this negative values of the same harmonics. So I'm at -0. Does that make sense? No, I don't have -0, right? I'm at -1 and -3. So this guy's going to have something at -3. Could be -2, I guess. -1, 0, 1, 2, 3. Now, if I talk about the alpha values at these different frequencies, let's say I'm going to talk about these alphas in the context of their magnitudes and their angles. Okay, so what's my magnitude at? Do I have a second harmonic term here? We said there was no second harmonic. All right, so these guys are going to be 0. But I do have a fundamental term, a DC term, and a third harmonic. What's my DC term in this series? 5. All right, so at omega equal to 0, n equal to 0, my magnitude is 5. Do I have an angle for that one? Does 5 have an angle?
0.
0. Or it could be 360, I guess. Right? There's many possibilities. We usually use 0. Could it have anything other than 0? If it was -5, what would its angle be? 180. Okay, that's important. All right. One of the tricks I'll probably give you on some tests at some point will be I'll put -6 sine 2 pi 180. Right? And you're going to tell me that C is equal to -6. Right? That's not true. All right. I can't have a negative number. These things are magnitudes that I put in front of these things. All right. If I have a negative number has an angle. All right. So we got to be careful about that. And maybe that's something I should really say for A, B, and C, all are numbers. They are real numbers. Alpha is a complex value. Okay. If the fact that A, B, and C are complex numbers, they got to be positive. All right. They should be positive. If I have a negative number on A, B, or C, there's an angle in there. All right. That's something to bear in mind. Okay. All right. So looking at this, we've got this stuff kind of all established. We said 2 pi 60 is this guy and 2 pi 180 is this guy. Okay. What's my magnitude of alpha at 2 pi 60? 2. All right. And then what's my angle at 2 pi 60? It looks like it's 60 degrees, right? Now, looking then at the negative frequency, -1 frequency, so -2 pi 60. What's my magnitude there? Well, look at the function. Here it is, right? So it's what? 2 is the magnitude again. What's the angle? -60. Okay. Because alpha is the conjugate. Alpha -1 is the conjugate of alpha 1, right? So they have opposite frequencies. All right. And then at third harmonic, that's 2 pi 180. What do I have at the magnitude at 2 pi 180? Well, it looks like it's 3/2, so 1.5, like that. And then what do I have at? So I've got 1.5. And then what's its angle at 2 pi 180? It's -90. -90. All right. Now, this guy also has a term at the negative third harmonic, so -2 pi 180, right? What's the magnitude at -2 pi 180? What's that? It's 3/2, right? So it's. Oh crap! Yeah, sorry. It was 6/2. Yeah, was what I had before. Thank you. Yeah, so it's actually. Yeah, it's actually 3, and this is 3. So this is -90, and this is 90. Yeah, sorry, I skipped to the result in the middle of my math. Okay, yeah, this guy was 6, so this should be 6/2. Okay. So what I did there was I did the basic approach that you guys are using right now to figure out the Fourier series coefficients. And in your homework, your current homework right now, homework 7, you would take those alpha values and then you would get C values and B values and A values and all that sort of stuff. And then you would use the Fourier series to graph this thing. So what I tell you to do is I tell you to say, well, give me X of t of the form, use those results to go from n equal negative infinity to positive infinity, alpha n e to the j n omega naught t. Right, you guys will use that formula to draw the graph, right? That's what you're doing right now. What I'm doing is I'm basically saying, all right, well, I want to go from X of t into basically something that just tells me at what frequencies I've got that information. So we said that guy is the Fourier transform. Once I know the alpha values, if I have a periodic waveform with this series, then what I do is I can create this Fourier transform using this relationship, meaning I take the alpha values and I plot the alpha values at the frequencies where the signal has information, okay? So basically, if I give you a periodic waveform, it's really not much of a step from what you're doing right now in the current homework. So I have my 3 steps here. I get my Fourier series coefficients, right? I map those to the appropriate frequencies, and then I figure out X of omega as the sum of those impulses that are located at those frequencies, okay? So if I go to what we have gotten to here, so let's see if I can just copy and paste this to another slide. Yeah, I can. All right. So if I look at this, all right, get this out of my way for myself. All right. So I get this guy right here. This was what we figured out for this waveform. What I want to do is I want to make the graph of this Fourier transform. So the Fourier transform was, this guy is X of omega equals sum n equal negative infinity to positive infinity, alpha n like that, okay? Now, how would I express that here? I don't want to draw that thing. I don't want to write it out. What I want to do is I just want to sketch it out. So this guy is got a magnitude X of omega. And he's got an angle X of omega. All right, the impulses tell me where I've got stuff. So tell me, what would I draw here? Given what I've got, what are the frequencies where I have information? Well, I already wrote them down, right? It's 0, 2 pi 60, 2 pi 180, negative 2 pi 60, negative 2 pi 180. All right. In the magnitude graph, I graph the magnitude at the frequencies where I've got information. So tell me, how many impulses am I going to have in this magnitude graph? How many impulses will be there for this waveform? In theory, it's infinite, right? In this particular case, it's not infinite. How many impulses am I going to have in this graph? 5.
5.
Yep, 5 of them. All right, and so I'm going to put 1 right here at DC. This guy's going to be with a height of 5. And if I do his angle is 0, like that. Okay, so I don't know what to draw for that. I'm just going to make a 0 because it's 0. Okay. Where if I move in the positive direction, where's the next place where I have something? Well, it's 2 pi 60. Right, so 2 pi 60, let's say, is here. So I'm just going to call this omega naught. All right, omega naught. This will be 2 omega naught, and this will be 3 omega naught. Okay, so this guy has an impulse that's how big at omega naught? 2. Okay, this guy's 2, and nothing at 2 omega naught. Then there's one at 3 omega naught. How big is that one? How big is that guy?
3.
3, yeah. And then they've got their little friends over here, negative omega naught, negative 2 omega naught, and negative 3 omega naught. They got the positive ones and the negative ones that stack up like that, right? What's that waveform always going to be? Well, it's always going to be symmetric around the y-axis there, right? Because it better be the case if this thing's made up of cosines and sines, it better be the case that when I look at the complex version of that I have coefficients that are complex conjugates of each other, which means the magnitudes are always going to map over. All right, now, what about the angle? So I had 0 angle at 0 degrees, but I also have something at omega naught and at 3 omega naught. So what do I draw at omega naught for the angle graph? What do I put there for that? So at 2 pi 60, the fundamental frequency, what do I put there?
60 degrees.
Yeah, this guy will end up being 60 degrees. And then there'll be negative 90 here. Now, without even looking at my table, I know that I should have complex conjugates, which means that the negative frequencies, what are the angles going to be? What's true of a complex conjugate?
The opposite of what you drew on the right side.
Yeah, you're going to get the opposite angle. So here at negative omega naught, I got something that goes down negative 60. And I'd have something here at 3 omega naught, which would go up to 90 degrees, like that. Right? So that's how I would approach making that kind of a graph. Now, in this case now, if I had something like asking you to plot that in MATLAB, okay? Because I'll ask you to make a plot of that. So here is me making that plot specifically. All right, that's the same plot that we just made by hand. Now, what I did to do that, here's a piece of code. Now, this is not a homework 7 thing, but this will be a homework 8 thing, right? Where I want to make these kinds of graphs. So when I look at this, I do my usual thing. I do a clear all there at the beginning, and then I define for myself my fundamental frequency. Okay. Now, what am I doing here? Omega equals this. What is that doing?
That's like your time vector in the time domain.
Yeah, it's like my time vector, except what I'm doing is I'm only the gap between things. It's going to start at negative 7 omega naught, increase in steps of omega naught, and end at 7 omega naught. So that means I'm going to have stuff. If I looked at what was in this vector, right? If I just created this vector and then I looked at it, right? I typed omega at the prompt and hit enter. What values would I see written out there for me? What would they be? Well, I mean, you guys thinking in terms of numbers maybe, but it'd be negative 7 omega naught. Then it'll be negative 6 omega naught, then negative 5 omega naught, then negative 4, negative 3, blah, 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 all the way up to 7 omega naught, right? That's what that vector would do. Then what I did was I created an alpha vector, which has the same size, and I plugged in there at specific points what the values should be. Now, you could have come up with a loop to do this that would be smarter than what I did. I just hard coded these values in. And these are the values that I did on the previous slide. Okay. What I then do is something I haven't done before is I use this thing here, this set of commands to make a graph of that. And one of my commands is this thing. I didn't do plot. What I did was stem. All right. So I have stem of omega comma abs of alpha. So let's see what you do know here. If I said abs of alpha, what is abs of alpha going to do?
The magnitude of the alpha vector.
Gives me the magnitude of the alpha vector, right? And so if I do stem, that's the new thing. Stem is just like plot. All right. What does plot actually do? Well, plot is you give plot a set of X values and a set of Y values, and it plots Y versus X. Okay. And what's it do? So if I say plot, if I told you plot 1, 2, 3, comma 4, 5, 6. Like that. What would plot do? What would the graph look like for that? So starting at 1, I would so 1, 2, and 3 at these locations on the x-axis. I would show the numbers 4, 5, and 6. And you would see a line between them. You didn't tell it that you had, so let's think about this. These are different things. Plot 1, 2, 3, comma 4, 5, 6. You said, I want to plot the numbers 4, 5, and 6 at the locations 1, 2, and 3. And what it did was it did what? It actually plotted infinitely many things between 1 and 3, right? What did it do? It did something called an interpolation. It drew a line in between the points that you gave it. You gave it 4, 5, and 6. It drew a line between them. STEM does the opposite. No, it doesn't do the opposite. STEM doesn't draw a line. So, like this. What would STEM do? Well, STEM would basically say, at each of those things, what I want to do is I'm going to say at 1, 2, and 3, I'm going to draw and say I've got the value 4. At 2, I'm going to say I got the value 5. And at 3, I'm going to say I have the value of 6. All right. STEM basically puts impulses at those points. All right. So we call them STEM plots because it looks like a little, I don't know, a little flower head on top of the stem, right? Is what it looks like. So when you look at it, it'll be a little tiny ball at the top of a stick, right? So it's a stem plot. So basically what this is trying to do is effectively try to show me a set of impulses. All right, so this is MATLAB's way of trying to show that, because that's an important thing to take a look at. So notice, I also use this thing here called subplot. Now, subplot, you may have looked at this. Some of you may have looked at it before. Subplot, what it's going to do is it's going to make two axes stacked on top of each other. So here is what a subplot looks like. This guy is the magnitude of x. This is the angle of x on the bottom. So this is, to generate this, this guy is subplot 2, 1, 1. And this guy is subplot 2, 1, 2. All right, this is confusing, the nomenclature here. You guys should be able to, for most things that I ever ask you to do, copy my code on this one. The subplot, I always forget it without looking it up myself. But what I think this means is that you want 2 rows of graphs in 1 column. And this guy is the first entry. This is saying I still want two rows of graphs, 1 column, and this is accessing the second one. All right, so if you look at my code here, subplot 2, 1, 1 plots the absolute value of alpha. Subplot 2, 1, 2 plots the angle of alpha. And notice I multiplied by 180 over pi. Okay. So what I have there is just sort of a recreation of what my code or what my logic did here. So we drew this out by hand. So we see that basically at omega naught, so at 2 pi 60, this guy had a magnitude of 2. And at 3 times that, it had a magnitude of 3, and at DC at a magnitude of 5. If I look at that, at DC, omega equal to 0, this guy's at 5. 2 pi 60 is right here. The magnitude is 2 right here. And 2 pi 180 is here. This guy's got a magnitude of 3. And then you can look, you can see similar things about the angles. Everything else, there's zeros because there's nothing at those frequencies. Okay. All right. I could say some more, but I'm going to stop it there because I'm going to overload your brains and you got a homework due. All right. So we'll look at more examples of this on Monday. All right. But this is one of the key things that we're going to be using in the project for sure.